Okay, welcome to Week 3, the Competitive Programming Club. Um, Today I did not have time for animations. I apologize, but the content is still. I'm just gonna do it on the board instead. But anyways, let's get to it. So, this week we're talking about trees, and we're gonna be doing like advanced stuff on like normal trees. So like um there's a few main concepts we're going to go over. The first one is pretty simple. So I'm going to go over it first. And it is called the diameter of a tree. So um, the diameter of a tree is the longest possible path. So it's a simple um, from U to V. So it's let's say path is the distance, right, then it's going to be the maximum overall U. Right? Um, and this shows up in a homework problem, Agamemnon's Odyssey, but uh, it doesn't show up in any of the problems we're going to go over today. Can you see that? Is that like kind of off the screen again? Anyways, so let me give an example. Um, like let me get a better marker first. But yeah, so let's take some graph. Um, so there's actually four tenders for the diameter in this scenario, right? Because you can go this length 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3, right? All those are the diameter. So let's change it up to be like this, right? So now um, diameter is going to be the longest path across the tree. So we just count 1, 2, 3. This is 1, 2, 3, 4. We can start here or here, and this outlines the diameter of the tree. Now, um, like I said, this shows up in your homework, and it shows up occasionally. But it's in order to find the diameter, there's a simple trick, and I'm gonna showcase it with a different graph. Um, so the way this works is that the one property of the length of a path um, from, or sorry, one property of the from a simple path is. Let me just explain like this. Let's say this is clearly the diameter here, right? Let's take up some point x off of the diameter. In this case, it's right here, right? If we were to take some path, or if we were to take a path from here to here, right? And we were to measure the distance from each point as we traverse along this path. So right here, distance is 1, 2, 3. All right, 1, 2, 3. And then as we get close along the path, the the path shrinks in distance, right? So now this is 1. If we're here now, this is 1, this is 2, until we get to here, at which point the distance from this off of the diameter and this point on the diameter has reached its minimum value, which is 1. And then after this point, as we continue along the diameter, that sharply increases, right? So we have a property here, and it literally looks like it visually. That's why I drew it like this. The property of of this path distance and path distance in general, like walking along the path and taking a distance to some point not on the path, it's convex, right? So that's the word that we use to describe. It's strictly increasing up to a point where it reaches its minimum, or strictly decreasing and then strictly increasing at a point, at that point. So how are we going to use this to find the diameter? Well, there's a simple lemma that states that the lemma goes like this. If you take some x on a tree. Now, remember, this is only going to work for trees. And what is another way to say it? A tree, a connected acyclic graph. Now, connected just means that you don't have disjoint graphs, right? It's one graph, right? Not two disjoint subgraphs. But acyclic is really the key property here, and it guarantees that the convexity property happens, right? Because like if I were to, you know, instead just a crude recreation, but if I were to instead have some loop here, let's say this is one single edge, right? And that's one edge, right? Then this property obviously does not hold anymore because there's a loop here. There's a different way to get to the target path. Okay? So we're operating on trees. And the lemma says take some x on a tree, so some node. Find the point farthest from x. Call it A. Then find the point farthest from A. B. A to B is the diameter of the tree. Now, think about this intuitively, right? Let's say we have some point on the tree, and we're finding the farthest away from that point. We know that it must lie along the diameter because the diameter is by definition the longest path. So like, if I bring up the example again. Right, so the oh yeah, that was, oh that yeah, you can do without the other one too, maybe. It's kind of glaring on the white. Okay. Oh, that is wait this one. Whatever. No, no, it doesn't matter. It's fine. So yes. So first of all, if x is on the diameter, right? The farthest point is going to be one of the ends of the diameter because it's already the longest path. Right? It can only be one of the ends of the longest path in the thing. If it's not on the diameter, if we were to pick some point that's not the farthest, or I guess really if we want to show the farthest point from any point x, it's always going to live on the diameter of the tree. Like, for example, if you were to try to extend, like you're trying to find some other example that prevents you from living on the other farthest path, you won't be able to do it without actually changing what the diameter becomes. So, like, we can try, like, yeah, I mean, there's two identical farthest points from here, so maybe I should reach this point. Like, there's no, unless the graph has slopes, right? There's no way that uh, if the diameter, by definition, the longest path, then any point on the tree that ends up that is the farthest away, like any path that is the farthest node that is the farthest away from some node not on the diameter is going to exit its non-diameter place, right? Because otherwise it would be a part of the diameter. And then that just collapses back to the case where we're on the diameter. It's already the longest path, so every you're going to end up approaching. Well, if it's the longest path from here, you'd be approaching this side. If you're here, then the longest path would be to approaching this. So, anyway, that's just. I don't want to spend too much time on this because it's just a random thing that. I mean, it's not random, but it's pretty simple. So how do you find? How would you find if you started at some point on tree? How would you find the farthest node from it? Anyone know? I don't know the optimal way. Well, I mean, just count the edges, right? But how are we gonna traverse the tree? Like traverse it. Right? So you're erasing this, but I shouldn't. If we're gonna start, I keep doing an example because obviously, if the point is just along the diameter, then it's true. But yes, so we do our depth first, and we just count, right? So just go 1, 2, 3, and then depth first search ends. Recurse back, 2, 3. Right. We have our well, in this case, they're both equally like. We'll just pick one, right? And then from this point, that's our A, right? Now let's find the farthest point from A. 1, 2, 3. Recurse back, 3, 4. And that's B. We found the path. We found the path from A to B, the diameter. Anyways, that's just that part. Now let's get into the real meat of what I wanted to show you guys today. So several things. Let's see what should do first. Let's do rerouting because that's going to be a little bit simpler. Okay, over. So I guess yeah. Let me start with the problem itself because that will provide nice context. So this is the problem. It's called the full depth morning show. Now, also remember, another skill you're going to need at IPC is to be able to parse these kinds of questions really quick. Well, all boring tree-shaped lands are alike. Well, tree-shaped lands, blah 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 blah. Usually, this first paragraph is not worth reading. Here we go. The region of tree land is made up of n cities connected to n minus 1 road, such that between every pair of cities there is exactly one simple path. So, I mean, implied by the name, but these properties should be screaming that this is a tree, right? Because first of all, if I have n nodes and I have n minus 1 edges, can I have any cycles? No, right? There's no room, no additional room for any edges for there to be a cycle. So we know that it's acyclic, but is it connected? Well, it says that between every pair of cities, there is exactly one simple path. Well, that means to get from anywhere else in the graph, There's no isolated part that I cannot get to. So it must be connected to the cyclic graph and therefore a tree. But let's go a little bit deeper. N is n minus roads. The ith road connects cities ui, bi, and has a pole of wi. So what does that mean? This means that we're on a gate tree, right? The edges have weights. Here's the main part of the problem. There are n minus one lucky residents from the city that sends them the fan mail. Each of these residents gets a distinct ticket to a different city in tree land. Okay, so we want to let's see. We want to where did okay, oh, sorry. I mean, we still don't know what the question is really asking it, so let's just keep reading. Each city in Treeland has its own tax on prizes. TI is the tax at the specific city, and DUV be the sum of tolls on each road on the only path from city U to V. So literally it's the weighted distance. It's just if DUV, let's say this is U, this is V, then it's just going to be 2 plus 5 plus 3, right? Let me draw the example on the board, actually. A good example. So we have 2, 1, 1, 1, connected to 5, 2 and 6. And then 5 connects to 4. 3 connects to okay. My graph drawing are poor, but you get the idea. So what is the thing now? So yeah, do D to V. So like if this is my U, this is my V, then D from U to V is 2 plus 5 plus 3, 10, right? So that's just the definition of that. So then the sum of the totals on each road only for a trip from city U to city B, the cost of that trip is then the tax from the starting point, the tax at the ending point, times the distance between the two, right? That should make sense, right? So the total, what we call this, just call it T. No, that doesn't. No, I have T. We call it cost, right? The cost U to V is basically this, but we also need to include uh, the text at the cities, right? So let's see. Let's keep reading. So the shock jocks. I mean, it doesn't really matter what they're talking about. Haven't quite thought out how much their prize is worth. They need to report the ranges, summarize. For each city that could win the prize, what is the total cost of purchasing all the tickets? So each city could win the prize, which the prize is from, remember, prize is the trip, right? And so basically they don't know where the winner is going to come from, right? So they need to calculate the cost for all the possible trips. It's going to be so like for like if they come from city 2, then the cost of the trip that they is going to be, well, wait, hold on. It says n minus 1 lucky residents from the city, right? So for each city, you're going to get a trip to every other city. It's because there's n minus 1 other cities. So what we're basically asking is, I need to find total cost from this node to every other node, right? The total cost from this node to every other node for every node. So let me just what it's saying is, for all u, then the cost of the total cost, call it total, uh, from u to v is just going to be the sum over all v of this tu plus tv times d of u v. Does everybody follow where that comes from? So remember, this part is saying we pick a node on the graph, finding the total cost to every possible node. Okay, so that's v being v not equal to u, obviously. All the other terms. Now we do this for all u, and then we literally just output that. That's literally what it is, right? Because 5 nodes, it wants this value for those 5 nodes. That's what the output looks like. So
don't we have to hold the start position of our summation? Like, don't you have to put from u to v on the summation? Because we're not guaranteed to start one.
wait, say that again, sorry.
Like, we can't assume that we're starting at 1. So don't we have to put from u to v on the summation? Or on the
We're just calculating the distance from u to v for all v not equal to u. So like if this is my u, then I need to calculate this value corresponds to 5 plus 2 times 2. Okay, that's this value here. And then I need the next v would be like that was my v for this guy. Now I switch to v to this, and I do the same procedure, and then I add it to this one, and then I can. So you see, so it'll just like shorthand. This just you'll see this all the time. Like if you're summing over a set, they just put the set in the bottom. Okay. Or like you could to be more explicit, I could put like v inside the adjacency list view if you wanted it like that, right? Just the graph is going to be represented as an adjacency list. So, right. So let's obviously we're just going to be doing the same thing 5 or u times, right, for the number and the number of nodes. So let's focus on 1. The first thing I want to do is take a look at that summation again. So the summation was for all v, we're going to have the tu plus tv times d of uv. Now, you can do some simplifying here, right? Well, first of all, let's distribute the distance across and break it up into 2 sums. So we're going to have tu times d uv plus the sum of tv times d of u to v. And now the second observation is that this is over v, right? Both these are over v. So tu is constant the whole time. So we can just pull that out, right? So we're just going to do tu sum duv plus sum tv. So really what we're looking for, this is already known, right? This is just whatever u we pick, it's just that t value there. What we really are interested in is now the sum of all the distances from u to all v, plus the weighted sum, weighted by the tax at each v of each of those distances. So naively, right, you will think, okay, well, for each u, I just perform this computation, right? So that's going to give you, let's say if there's n nodes and there's n minus 1 edges, and you can pre-compute these distances, right? So we'll call that, those distances will be, it'll take O of n, right? Because we already know how to compute distances with the depth first search, right? So you're just going to, instead of counting 1, 2, 3, 4, 5, you're going to be counting +2 or +2 +6 or +2 +5 +3, right? You just do it weighted. So that's O n. And then there's another O n. Actually, no. Well, yeah, the sum is going to be over v, so that's going to be O. It's going to be n plus 1. So if we compute this, right, then we can just look it up in O of 1, but we still have to do it v times, so that's still O of n. And then this is another O of n, right? Because we call D, think of dv as like a two-dimensional array, right? Just a two array that we did that work ahead of time. So then, but then we have to do that for all u, right? So that's going to be another O of n. It's going to be a total of n squared, right? Everybody's following why the time complexity is n squared? So that could be fine, except look how big n can be, 100,000, right?
Oh, because oh,
Because we have to do it over all u. So, right, yeah, that's exactly right. So the this is 10 to the 5, right? So yeah, 10 to the 5. If we remember from our um, simulation checklist, from week 1, let me pull that up. Simulation checklist. Let's see, what is it? Is it 3? No, 1. How is it? Yeah, take a look at this. If n is 1, if n is 100,000, then you can choose between n log n or n necessary for this. Remember, this is for C++. So if you're doing it in your own language, you'll have to. It's much harder to do that, to understand the ballpark estimate in a language like Python, understand how the interpreter works, which I don't. So I use a compiled language like C++. And then I can do this to go back. All right, so yeah, n squared, but we need n log n or n. We can actually do it in O of n, and I'm going to show you how. So let's do, I mean, finding the distances should be pretty trivial, right? Like you just do a depth first search, grab the weights, and grab the sizes and all that. I mean, grab the weighted distances. But we're actually going to want other stuff in the meantime to prepare for the um, trick. So that's going to allow us to do this in O of n. And I want you to think about, I guess I can start from playing the recurrence relation. So this is going to be using dynamic programming over this tree in order to be able to do this in O of n in 2 passes. So we're going to do 2 depth first searches over this tree. I'm going to go over the second depth first search first, and then we're going to go over the first depth first search after that. So the recurrence relation is, let's assume that we have already computed the total sum, right? We have the, let's call it S of u is going to be equal to that sum that we mentioned. The TU sum DUV plus sum TV DUV. Boom. And let's say it's of U. Okay. Okay. So what I want you to notice is think about what happens if we were to slide U like this. So we move our U from here to here, right? What changes? What will change about S of U? This is actually the value of SU when we U. Actually, let's call this V. So S of V is going to be locally different from U, right? In fact, everywhere on this graph, transition from U to V, this sum changes in a predictable local way, right? And let's think about what happens, right? So now this is an unusual way to draw a tree, but if you just imagine drawing it instead like this, it's pretty obviously it's a tree, right? So, right, you can see U is this is U, and this is our V, right? So when we slide from U to V, actually, you know what? I'm gonna switch U and V, or I'm gonna change them because to make the example more illustrative. So we're gonna start here, and then we're gonna transition here. Okay. So we're starting here. Well, then I'm gonna have to redraw the graph, right? So if this is a root of the tree, then the tree is gonna look like this. Right? So this is our U, this is our V. Right? Does that make sense? Did everyone understand how I got from this graph to this graph? It's the same graph. When I reroot the tree, is what this technique is called, it's gonna look like this. Can everyone see how the rerooting works? Did I do that right? Yeah. So what we're looking for, right, is some local way to describe the change in the sum, right, which remember is literally just plus, 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 plus to this. So what changes, right? Well, everything in the subtree of U that does not contain V, right? So everything, or let me put it this way. V and everything in the subtree of V on this graph, right, is going to get closer by whatever this weight is, right? So this is our weight W, right? Everything in here, when I transition to V, right, the sum is going to be W closer, right? Does that make sense? If you want, I can like literally explicitly draw it out, right? So if this is U, right, then S of U is going to be uh, let's just not worry about this part. Let's just worry about this part because the process is identical for both. So let's just worry about the distance, right? Um, so S of U is going to be 2 plus 6 plus 5 plus 5 plus 3, right? Okay. Now let's take V. As V is be 3, I'm gonna write it weird, but 3 plus 5 3 plus 5 plus 5 plus 2 wait, 3, 5, 5, 2, 5, 6, right? 6 plus 5. So, um, so what changed, right? So we lost when we I did it right. So 5, 2, 5, 6, 5, there's 3 5s, 3. Okay. Yeah. So yes. So everything when we switched from U to V, right? The distance, all V and its substring right here, lost 5 each. They lost 5 weights. We traversed closer there, right? And you can just see it like let let me if I were to take f of u and I were to subtract 5 and subtract another 5 for each of these members in this subtree, right? But then at the same time, when I move this way, now these 3 nodes have increased by 5. Do you follow why? When I when I shift, when I reroute the tree, some of the nodes lose a weight and some of the nodes gain the weight. So we have minus 2 5s, but we have plus 3 5s. Okay. And then obviously that's going to give you a net of just an additional 5, and that's reflected in the sum. So does that make sense? So what we need to do is,
Which is for the first sum, right? What about sum of T?
you mean the TV times the DUV?
Yeah.
Well, if we can compute DUV, all we have to do is multiply it by TV, right? For each, and then add them all, right?
Yeah.
For each TV, right? So really instead of keeping track of the um, distances, we'll be keeping track of the t-weighted distances. So we're two arrays, pure distances and then t-weighted distances. And you'll see that it will be reflected. But yeah, so this is the main recurrence. But how do we calculate that? All right, so we need to keep track of the number of nodes in the subtree of V, including V, and then consequently, everything outside of the subtree will just be the total number of nodes minus the number of nodes in the subtree, right? So n minus, we'll call this size of V, okay? So think about it. So S of V, let's write it as a recurrence relation now. S of V is equal to S of U, right? Plus all of the weights that let's do it like minus all the weights that we lost going into V. So that would be the size of V times the weight that we lost, right? So because in this case, size of V is 2, we lost 2 5s, and the weight is 5. We'll call this, the weight from U to V. Or actually, how it's defined in the problem is that the weight, no, is it defined that way? Doesn't matter, we'll call it U for now. But then we also gain a weight from everything not in the subtree. So it's going to be n minus the size of V. that make sense? So we lost some and we gained some, and this is how much we gained. Now, doing a little bit of simplification, we have W times N minus 2 times the size of V. And that is the recurrence relation. So, oops, wait. This would be plus, okay? So this is our recurrence relation for the local changes in the total sum across a tree. Why do we care? This is great, right? Now we can just start at some u, right? Any u, do our DFS, calculate S of u, and then we just have to do another DFS, which is going to, for each node that we traverse locally, right? If I go from this guy to this guy, we're going to apply this relation. And then when I go from this guy to this guy, we'll apply this relation. And when I go from here, we'll apply this relation. And then, key thing here, if I go from here to here, we're using this guy's S value to calculate this guy's S value. Let's call this P and Q, right? So we're not going to keep using S of U for this guy over here because that's not going to hold. This relationship only holds locally. So, but this is the beauty of dynamic programming, is that we can just keep track of it, right? And then we can we're saving so much compute time, recomputing the same thing over and over again by holding on to that value and exploiting this local relationship in the total sums. So, and then I'm not going to show um, the tax T weighted one because that's the same process, but instead of subtracting n minus, you'd subtract total T minus the subtax. So along with the size, actually, I didn't go over the first step for search. That's also important, right? We need to define our, so remember, we need to keep track of size of a subtree. We need to keep track of the tax of a subtree for the weighted instances you're talking about. That we're going to call that tax. And then we need our S of U, and we'll call it TS of U, which is the tax weighted sum. And then literally what we'll output at the end is literally just TU SU plus TSU. That's the final answer. So we got to keep track of the size of tax SU and TSU. How do we do that? Well, we can do that all in one depth search, right? We're going to do it all in one depth first search. And how it's going to work is, this is like, if you're not used to recursion, it might be a little tricky, but I want to simplify it. So so how DFS works is we're going to have, I'm going to skip a lot of the technical stuff, but so for node, just call it for node in the graph, right? We're going to set its size, so the size of that node, we're going to set it to 1. Base case kind of, right? And we're going to set the tax equal to the tax at the node. And then we're also going to keep track of SU, and that's going to be, or sorry, instead of using SU, it's going to be plus equals the tax value. Oh wait, plus equals the current. So I forgot about that. We need the distance from the root, right? Because remember, this is a tree. It's a weighted tree. So this is we're not calculating depth. We're calculating distance from the root, not depth from the root. Okay, so think about it like this. Let's start off. Let's call this DFS with node parent and distance. And then we'll call DFS with the parent of the parent, and the distance. Okay. And so sum of the node is going to just be plus equal this part. So T of the node times, I gotta stop using my finger, times the distance. And then finally, oh, sorry, no. That's TS, obviously, because this T, and then S is the unweighted distance. Okay, so if we're going to initialize, these are all going to be zero initialized. Right, so don't have to worry about like corrupted. They're all zero, and then we're going to assign for each one. So it makes sense if you think about the root, right? Obviously, the root size is 1 for now, and then the tax is going to be, or don't think about the root. Think about a leaf node, right? Think about going all the way to the end. You got a leaf node, size 1. Tax is just the tax of that value. The current tax weighted distances is just going to be its distance from the root times the tax at that node, and then the unweighted distance is just the distance from the root. Now here's a recursion. So we'll do for neighbor in call it neighbors of the node. Okay. For neighbor and neighbors of the node, first of all, if the neighbor is the parent, this is why we keep track of the parent, right? Then we're going to skip it because we don't want to go up the tree. We only want to go down the tree, right? From the root downwards. So we're never going to go the tree. But if it's not the parent, then we are going to reverse with the neighbor, the node as its parent, right? And then we're going to take the current distance plus, sorry, so this is name, but it's also got a weight, right? Because this is a weighted tree, so every edge is going to have a weight to it as well, plus the weight. Right? That makes sense? Because we have our current distance from to the node. Obviously, for each neighbor growing downwards from the node, it's going to be the distance plus the weight of that edge, right? The weight of that edge to that. Now, what is that going to do? Think about it. We're going to go all the way back up, and we're going to initialize our size and tax, and then let's assume we're at a leaf. It's going to have no neighbors, right? We're going to just return back up. But remember, this size is outside of the recursion, right? So it's going to persist. So every time we set the size, it's going to persist. So we go all the way down, recurse back, and now the size of this node is populated with information. So when we exit out of the DFS and we start popping up back up the tree, we're going to be in that got populated here is going to be added to the value of the node. So think about how this recursion works. Okay? My favorite way to think about recursion is to just not think it too hard, right? The magic function that's going to tell me the size and the tax of the subtree at that node, right? So just it's going to do a bunch of and it's going to come back and it's going to have those values sorted size and tax. Then this all the elements in that tree. Well, if the size of the node is going to represent itself, 1, plus um, all of the nodes in its subtrees, right? So that's why we add, after we've populated everything, it comes back up, size of neighbor, fill that information in it. And then same with tax. Node is going to have the tax of the neighbors. Okay. So make sure that makes sense, right? The DFS tells you the values from the neighbor downwards. And then you add that to the current node, and then you get the value of all of that information in that subtree. Right? So, and that's the whole DFS. So this is the first DFS, right? The second DFS, I'll just go over with the code. I already basically explained the recurrence relation. So I did the second one first, but now I did the first one. So now I'm going to just switch to the code, which is this. Yes, I remembered. So let's take a look because this is important actually. Let's go back at the format, right? This is going to tell us we got to look at the sizes of things because we have to determine how big. We don't want an integer overflow, right? So we're going to have to determine the sizes of the types, right? So for say you can just use long in general, but you don't have to use long, then don't. But we're going to be summing over potentially 100,000 nodes. The sums should be longs, right? This should be 64-bit integers. But let's take a look at the format here. So we have n. The first is n, which is going to tell us how many nodes. And then the next n integers are the taxes for each city. Then the next n minus 1 is going to be who connects to which I connects to which v, and the weight of that edge, right? Pretty straightforward. So how do we parse that in C++? Well, it looks like this. I have our n, read it in, form our this. Sorry, this is not tax. This is the not the taxes, right? This is the visual tax C, all right, not the tax tree. Then we need to calculate our total tax for the recurrence relation. Remember, when we did remember, it's called rerouting because we're switching the root and we're using that local change and dynamic programming to do an O of M. We did n minus 2 times the size of the subtree. But when it comes to the taxated version, we don't care just about the number of nodes. We care about the taxes at each of those nodes as well. So instead of subtracting from n, we subtract from the total tax, which is just n times, or it's the n additions of each tax. So that's literally what's going on here, right? We read in the tax for I, and then we add it. This is just a edge struct, right? And this is our tree, which is going to have n nodes, and it's going to have a list. It's an adjacency list, right? So it's going to have a list of edges coming out from each node. And then for each edge, each n minus 1 edge, we're going to grab who goes where and what the weight of that is. Now, what's this? Might look a little esoteric, but it's literally just the fact that the nodes are 1 indexed. See, the nodes are 1 indexed, but I don't want to deal with that, so I'm just going to subtract 1 for all of them. Okay. And then remember, this is a directed graph. It's undirected, so every time we add an edge going out from one node, we have to do the same other edge, right? So we're pushing U connects to V with weight W, and V connects to U with weight W. right? Makes sense? Okay. Then size, tax, some distance is our S, and weight of distance is our TS. Okay? Now here's our first DFS. This is going to look pretty identical to up here, right? Set size to 1, set tax to the current tax, add to our sum distances and weighted sum distances for the root. Yeah, that's a mistake. It's not, we're not updating it. We're only updating it at the root. That's, yeah, that should be clear. Right, because this DFS only concerns us with the value of SU. In order to get the value of S, all other U's, or all other V, yeah, all other U's in the graph, we're gonna do the second DFS with the rerouting. So this DFS, literally, we're just doing it from a fixed point, find all the information. So then here's that model, right? Here's that loop. Neighbor cost for tree and node. And then if the neighbor is the parent, skip. Otherwise recurse. After the recursion is all done, said and done, it fills it out and then it comes all the way back up. And then we fill in our size and tax information with the size and the tax information from its subtree. Now here's the cool part, the rerouting. It's very simple, right? So we just take the each of the edges. We're doing another DFS, right? So we're just going from the parent down. And obviously, if the neighbor is a parent, we don't want to go back up the tree, so we skip. And then we do our recurrence relation here, right? So the distance S of neighbor is equal to S of the current node plus the weight, called it, times n minus 2 times the size. LL is a macro for long. Same here. This means long. And this is because n is originally an integer, but we don't want it to integer underflow when we do this subtraction here. So we cast it to a long. You could just also write long for n as well in the first place. So weighted sum is literally the same thing, right? The weighted sum of this neighbor is the weighted sum of the current node plus the cost times the total tax minus 2 times the tax of the subtree. Okay. And then we reroute and we DFS. Okay. And literally the solution is just do the first DFS, do the second DFS, and now we output this value for those. Okay. And that's it. That's literally it. So if you want, like, just we can watch the fun check marks. It's not that fun because it's just like it's more anxiety inducing than it is fun. But look at that. Accepted. So that took me way too long to explain. Or maybe we just don't have enough time. But I really wanted to go over tree number generator as well, because that's another really important concept. However, I won't be able to do that because it's 7. But I wrote the most fucking detailed this explanation of everything that's going on in literally, if you just read the answer down, you will understand what's going on. There's a lot of concepts back to back, but it doesn't really require any like super creative or like gotchas. It's literally just straight down algorithms. So I might go over it actually next week because this is like really important. But yeah, that's all. Right? If you wanna any question or anything, but
Remember, is A star pathfinding of N for N nodes?
I don't know.
That one, like, I don't remember.
I think so because I think it literally is a greedy algorithm that just goes on a
the
heuristic.
cheapest style.
Yeah, I think it is Oven because Dijkstra's gives you the guaranteed answer in n log n. So why would you do anything except faster?
I feel like there's gotta be a solution.
Simple solution?
I was thinking,
What do you mean, like a simple solution, like the
simpler
heuristic?
solutions.
The problem that we just did
Yeah, I was
in Oven, well, A star doesn't give you the right answer every time.
no, but that's because of the taxes. And
Well, A star in general doesn't guarantee the correct answer.
but I would,
A star is a heuristic algorithm. It's not a guarantee.
yeah, but I was gonna traverse the whole tree,
Okay.
store in a set the distance from a chosen root node to each other node,
Okay.
using a star to include the optimal taxes, because there might be some.
You don't need A star to do that. You just need a DFS.
Well, I I think in my head I came up with a reason why it needed to be A star, but I am doing now. But I think you store a root node that you choose. You can store the amount or like the total weight from A to B, including the taxes. So you would add the tax of your start and your destination to every other node in a set. And
You're traversing A star is about finding the shortest path, right?
yeah, I
So
think
if you have to, yeah, A star is just a DFS plus a heuristic.
so like why can't you just grab the okay, this is why. Because if you so the idea was you have everything in a set, all the distances labeled out from like 1 to 2, 3, 4, 5. And if you want to figure out the distance from 3 to 5, you just take 1 to 5 and subtract 1 to 2 from it, and then you get 3 to 5, which is where the taxes mess you up. Because
Well, remember that only works. You're saying just like shift it, subtracting from this point, right? Or whatever is to the left, right?
yeah,
But that's essentially what the subtree idea is, right? But you have branching paths out this way, then you can't just subtract the distances. I mean, you could literally go from each point, subtract it, and subtract it, and then you'd have to account for the overlapping paths, right? But then again, it's not going to be O of n anymore, right? Because that's going to be multiple DFSs that you're going to have to do.
I think I have to draw it out. I don't think
That's
I can
fine.
visualize it fully, but
I mean that what I it's O.
Okay.
It's literally like
like just O of n.
yeah, it's just O of n.
Because like the one I was thinking was like there's like 2 O of n, O of 2n.
So on that the problem you are grading roots. It's been a while since I went over ABL trees. Do you know if it's related to that at all? If I remember ABL trees, you do a bunch of rotations.
Yeah, I mean the only thing that's really similar to the AVL tree is the like rotation. Yeah. Like, and even that is just for a visual aid. Like a AVL tree, because AVL tree is a type of binary search tree. The goal of the binary search tree is so that everything in the left subtree is greater than everything in the everything in the right subtree is greater than everything in the left subtree for each point in the node. That way, if you want to, it allows you to search it for a given item in log n, and then if you want it to turn it into a sorted list, you can literally just pop the tree.
Yeah, and you also can also see the balance with rotation.
Yeah, the balancing is why red black tree is more commonly used in AVL trees, because its balancing algorithm is better. Because remember, the only way that a binary search tree can be log n lookup time is balanced. Because if it's truly unbalanced, like think about the worst case, it's literally just a singular line. Yeah, then that's just O of n, right? And then the difference between a binary search tree and a heap just cares about the parent is bigger than its children, or the parent is less than its children, depending on if you're doing max or min heap. But binary search tree wants it to be literally sorted all, and that's the difference between those two. Anyways, Cool. The other problem that I didn't get time to show uses that binary trick that we learned a while ago. Remember that where we break it down into the bits and then do the lookup table and stuff?
Like that.
It shows up everywhere. It's like the most ubiquitous pattern. It like I didn't even know it's hiding in plain sight. It's crazy.
Yeah.